finally getting to a video I've wanted to make for a long time on inverting distance matrices using classic multidimensional scaling, which I'll spend most of my time on, and also a little bit about p-stress towards the end, an alternative technique. And this is really a follow-up video to another video I did on distance matrices. Let me just talk about those again real quick. So given a point cloud, and this is an example of Euclidean point cloud, this figure 8 here, so I have this in the Cartesian plane. So given a point cloud and a notion of distance between the points, in this case a straight line distance, I can create a square matrix that has as many rows and columns as there are points in the point cloud. And given some ordering of the points in that point cloud, so I'm indicating that with this color map here, and I'm going around the parameterization of figure 8, so the first point would be this one in red, and then the last point would be this one in blue. So given that ordering, then I can compute all pairwise distances and lay them out in that order in this distance matrix. And so what you can see here is I've highlighted a couple examples. This blue pixel in the distance matrix corresponds to a local max in the distance matrix, which indicates that point 0 is very far from point 50. So here's point 0, here's point 50. So you can see that those are very far, so that would lead to a large value in the distance matrix. And by contrast, here's an example of a min in the distance matrix. So point 25 or so is fairly close to point 75, and that's where we get this pinching in the figure 8, where it would actually starts off like this, then goes around, and then gets close to itself again. So we see a local min there. Now, what I'm going to be focusing on in this video is actually going the other direction. So rather than starting with the point cloud and computing the distance matrix, I'm actually going to say, given the distance matrix, I want to go the other way and invert that and come up with a point cloud, a Euclidean point cloud, in fact, whose pairwise distances are as close as possible to the distance matrix that I gave. And so this is where I'm going to pull in the techniques, either classic multidimensional scaling or inverting p-stress. Okay. So those are the techniques that I will talk about. Now, why would I want to do such a thing other than being kind of a mathematical curiosity? You know, we often want to try to talk about inverting things. But there are some very practical applications here. And one of them, this is from a survey that I gave my students years ago when I was teaching a applied geometry class. I asked them to rank academic subjects by similarity, where they were very similar if for a low value, and high value indicated that they were different. And so this was kind of the average consensus of my class. But it's actually maybe better for us because we evolved with a spatial sense that we're very attuned to. Maybe a little bit easier qualitatively to look at a point cloud that somehow captures the distances that have been specified here. So here I see that CS and EC are close to each other, and they're both far from art history. And that's certainly reflected in the numbers in this table, but this, I might be able to look at this and immediately understand a lot better what the similarity is between these. So this is used pretty often in psychology when qualitative studies are done to come up with a spatial representation of the results. Another kind of qualitative example is something I used to give in an assignment in my data structures class, where I would have them rank some category. This year it was pop stars. And then there's a notion of distance between two different rankings, and from that I could actually show who had similar tastes by laying them out in a grid. So I'll go through that example. And then finally, I mean, there's lots of examples, but another example I want to touch on that's quite different from the other ones is you can use this technique to come up with a canonical representation of 3D shapes, so that they, even if you bend around, so I'm a human and I'm in different poses, even if you do that, you still get the same canonical shape that you can then match. So I will show the code to do that. All right. Now, you should probably go back and review the distance matrix video if you're a little bit rusty on that concept, because I'm going to be taking most of that for granted. So I've actually taken this code and copied it basically from the last video, tweaking the point cloud a little bit to prove a point. But just a quick review, we're going to start with Euclidean point clouds, where you can measure the straight line distance as the square root of the sum of the squared differences between the coordinates of 2 points. So that's the distance we're going to use. And I showed this is how you can do it naively from the definition. But actually, I then showed that there's a nice algebraic trick you can do. If you look at the squared Euclidean distance matrix, then you just FOIL and combine like terms, and actually you can split that computation into 3 parts, which is very succinct to write in NumPy, and it takes advantage of broadcasting and matrix multiplication to compute the distance matrix much faster from a point cloud. So if I'm given this matrix where the point cloud is specified with each point's coordinates along its own row, then I can do this very quickly with this broadcasting and matrix multiplication. All right, so it turns out this trick of computing the square distance matrix very quickly is a great starting point algebraically to go backwards from the square distance matrix back to the point cloud that we're looking for. So let me define a few matrices, then I'm going to write this algebraically and work it a little bit and try to go backwards. So let me define some matrices to help me out here. So I'll say, given a point cloud with n points in d dimensions, actually we're going to start with Euclidean point cloud. So we know that we're measuring the straight line distance of points that have d coordinates. Okay, so given that point cloud, we're going to represent the point cloud with a matrix called X. So X is a n by d matrix, where each point is along a row. All right, so each point has d coordinates. I put those d coordinates along each row, and I have d columns total and rows total. Okay, now I have to come up with a matrix that does what this term here does. And so I'm actually going to rename this to G. This is the best name I could think of. This is the squared magnitude of each point, and it's laid out along a column vector. So I'll update it here in the code so we keep this parallel here. So I'll say, let's let G is a n by 1 matrix, where G, the ith row, and then 0th column, there's only one column, is equal to the sum of the squares of each coordinate in the point. So that's what that is. And then finally, I need a matrix. This is more notational than anything, but I'm going to define the matrix, we'll call it 1 sub n, as a n by 1 matrix of all ones. So in NumPy, this would be, np.ones and 1. All right? More notational than anything, but it'll help me to turn this into an algebraic equation. So now what I'm going to do is take these 3 matrices and use them to write what I have written in code here out in matrix form, which is going to be almost exactly like this. But that will then help me to do some algebraic manipulations to try to solve for x in terms of this. All right. So if I write this down as an equation, I'll say here d squared. So the squared distance matrix is equal to, okay, so first what I have to do is this here is taking this column matrix and repeating it n times. So this is going to broadcast this column matrix n times. So in order to do that, that ends up being the matrix multiplication, which is G times 1n. So if you think about it, oh, I'm sorry, G times 1n transpose. Okay. And so this is the column matrix G times a row matrix of all ones. And so that row matrix of ones takes each column and repeats it along n times. Now I'm going to do a similar thing for this second term here. This is a row matrix of the squared magnitudes. And I'm going to want to broadcast and repeat that row matrix down n times down the rows. And so that's actually just going to be the transpose of this whole thing. So that's going to end up being 1n times G transpose. And by the way, I should take this as an opportunity to point out a very important fact. So I'm going to say note, AB transpose is equal to B transpose A transpose. I'm going to use this fact over and over again. So pay very close attention to this. This is a fact about matrix multiplication, and it's related to a more general fact about algebraic groups. Okay, but anyway, so all right, so we knocked out these first 2 terms, and actually the third term is quite easy. This is just a matrix multiplication. So that's going to be minus 2x times x transpose. Okay, so there is my algebraic equation that expresses exactly what I did in code here. The only really trick was to think carefully about how I could accomplish this broadcasting here with a matrix multiplication. Okay, but now that I have this in a form, I can reason about it a little bit more easily by applying things to both sides of this equation and then eventually, hopefully, isolating x by itself. That's my goal. And so to that end, I want to define something called a centering matrix. So define a matrix H, which has the effect of subtracting off the mean of a vector from all of its coordinates. So in other words, given a vector, so that is, given a vector v, which I'll express as a column vector, that's, we'll say now it's an n by 1 matrix. H times v should do, it's easiest to write really in NumPy, should give me v minus the mean of v. All right, so I take the mean of v and subtract that off of every coordinate of v. Okay, so let me try to make a matrix that realizes this property. So I'll call this H. This seems to be a convention. And first of all, okay, it's going to be in two parts. The first part, it actually just takes whatever vector as it is. So that's going to be, I'll say, the identity matrix with n elements. But then I have to subtract off the mean from every coordinate. So first I need to think about, well, how do I compute the mean of this vector? And in order to do that, I have to sum up the elements of the vector and divide by n. Well, if linear algebra-wise, I can write that the sum as a dot product with that vector of all ones. And so to write that, that would be the vector of all ones transposed into a row times that vector v, right? So if I just look at this by itself, this is actually going to be a scalar or a 1 by 1 matrix. Row matrix of all ones times this column matrix v. That will just sum up the elements of v. But I do also want to divide this by n, right? Because that's what actually gets me the mean. So I'll make sure I divide that by n. But I need to, okay, this is a little bit cheating. I don't have this magic broadcast from NumPy when I'm dealing with actual matrix equations. What I need to do is take this 1 by 1 matrix and repeat it along a column so that it gets subtracted from every element in V. So in that case, all I have to do is just multiply this 1n again as a column vector by this whole thing. And actually, let me fold this in here. I'll just say, okay, this should look good here. All right. So yeah, and then we're going to multiply this whole thing by v. Okay, yes. So this is what we do. And actually, you'll notice this really, if I'm going to write this in code, it would be written as, which I'll do in a second actually. In fact, I'll just start doing that down here. So I'll say, okay, n is equal to square distance, however many rows there are, which is also how many columns there are. And so I can define H if I'm going to naively follow the definition here. That's going to be the identity matrix, which is awesomely defined as I, with n elements, and then minus 1 over n times. Actually, this is going to be a matrix of all ones if I look at it. Right. So the column vector of all ones times the row vector of all ones next to it on the right is going to be actually a matrix of all ones. So that matrix turns out to compute 1 over n times the matrix of all ones. That is a matrix that will compute the mean of a vector and repeat it along every single element. All right, so then we just subtract that off from the vector. Okay, so this is called the centering matrix. Awesome. So why do I care so much about this? Well, this is going to help me actually in a few ways. One of them is it's going to simplify this equation. So let me first start by multiplying on the left by the centering matrix on both sides of the equation. So if I multiply by the centering matrix on both sides of the equation, let's think about what that does. Now, I reasoned about H as what it would do to one single column vector, but when we multiply H by an entire matrix, it'll just do that to each column in the matrix in turn. And so this is going to be, we see here this multiplying by the left of my square distance matrix is equivalent to multiplying on the left by H in these three parts. And actually, this is going to kill the center term. So if you think about the center term, this is repeating this square magnitude row along n times, stacking that row down. What that means is each column is a constant, right? So if I had a row ABC and I stacked that, it would be ABC, ABC, ABC. The first column would be all A's. The second column would be all B's. The third column would be all C's. And so subtracting the mean of each column from all the elements in the column is going to give me 0 in every case. And so I can simplify this, actually, by just cutting out that middle term. And what I like about that is I'm getting closer to getting just x by itself on one side of the equation. Now stop for a second and think, okay, how could I do a similar thing and get rid of this term as well? And the answer is, I can actually multiply on the right by h. And probably really correct to think about this correctly, we're really multiplying on the right by h transpose, although this matrix is symmetric, so I'm just going to write that as h. But really, the reason I said that is because I wanted to think before as subtracting off the mean of the columns from all the columns. Well, but if I multiply on the right by h, that's going to subtract the mean off the mean of the rows from each row. And so what that does for me is that takes care of this other term here. And so now I'm left with just a term involving x here and its transpose. And so let me now try to get that by itself on one side of the equation. So I'm going to move things around a little bit. And I'm going to use that okay, so first I guess what I'll do is I'll just divide both sides by -2. So I'll say here this is going to be -1/2 this on that side of the equation. And then I can use, okay, matrix multiplication is associative, so I can change my parentheses here a little bit, and then observe that that actually, as I said, this h is its own transpose. So really, I can write this as h is symmetric matrix. I can write it like this. So I didn't change anything about the equation. I just used the associativity of matrix multiplication, and then the fact that h is symmetric. But now I can go back and use that rule that I said a moment ago, that the quantity AB transpose is B transpose A transpose. And I can see that this then is actually HX quantity transpose. Okay, after this manipulation, we're a lot closer to getting x on one side of the equation. In fact, what we have is HX. In other words, doing the column centering on each column of x. And if you think about it, what that's saying, because of the way we laid x out with each coordinate along its own column, that's saying subtract off the mean from each column. And it's really much easier to explain what this is geometrically. So here is x, the original point cloud. And what hx is going to do is translate that so that the mean of each coordinate is 0. Or in other words, translate it so that it's centered at the origin. So here is an arrow showing what the translation will be. In this particular example, the center happens to be around the pinch point of this figure 8. And so that is what hx is doing geometrically. So what we'll be able to solve for is not x directly, but a centered version of x. And that's actually completely fine, because that still captures all the geometry that we're looking for. It may even be desirable, especially if x is way off there in space. So yeah, so not only does doing this double centering have the benefit of killing off these terms and isolating this, it's also going to allow us to solve for something centered. So it's a nice side effect. Okay, so let me write down what I have so far in code. I'm saying that if I do this, if I say 0.5 times h dot d squared dot h, if I do that matrix multiplication and divide it by -2, I'm saying I have this matrix here. Now how do I go further and actually solve for x? Because this is, or hx in this case, this is not hx directly. Well, I can see in this form it's a very special kind of matrix called a Gram matrix. So say note, hx times hx transpose is a Gram matrix. And this has a few properties that are useful. The first one I'll talk about is a more general property of symmetric matrices. So among other things, it is symmetric, so it's its own transpose. This means we can use the spectral theorem to factorize it into an orthonormal basis. Okay, my head's in the way. Into an orthonormal basis. So just to write that out in math, what I'm saying is I can take this hx times hx quantity transpose, and I can do an eigenvector decomposition of this so that it can be written as u, I'll say us u transpose here. Okay? So this is an eigenvector decomposition. So in this case, I'll say where where columns of u are, or I could just simply say where u is orthonormal. And we'll say without loss of generality, the diagonal elements, so S is a diagonal matrix, diagonal elements of S are in decreasing order. All right, so that's the spectral factorization that we're going to do. But the Gram matrix has another property which is really helpful for us here when we're trying to solve. So the Gram matrix in particular, it's a very special kind of symmetric matrix where it happens to be positive semi-definite, which means that the eigenvalues, or in this factorization I've written here, the elements, the diagonal elements of S, are non-negative. Okay, that's really useful for us because what we can do is take this equation, and because the elements of S are non-negative, we can take the square root of S and actually factorize it so that this equation can be written as, when I say S to the 1/2, I'm taking this diagonal matrix S and just taking the square root of all the elements. And I can see that S, doing that, S to 1/2 times S 1/2 is S. But what's really useful about that is I can suddenly make it look a lot more like hx times hx transpose, because it's the same kind of trick, right? I can say, all right, well, this is us 1/2, and then I can take out these two terms here, use my little transpose rule, and say, well, yeah, that's also us 1/2, but transposed. Okay, so now let me just summarize what I've shown here. So at the end of the day, I've shown that I have an equation that says that hx transpose, if I've done the factorization of that matrix into the spectral decomposition and group the terms like this, then I have this equality. And so it almost looks like I have the solution right here, right? If I manage to compute this spectral decomposition, then I can take the matrix U and multiply it by S to the 1/2. But there's a couple things that I need to be a little bit careful about before I declare victory. So one of them is that the dimensions of this matrix are a little bit different from the dimensions of hx. If I think about, so let's just write this all down. So h is n by n, but x is actually n by d. So therefore, hx is n by d. But in this factorization, u is n by n. So we're asking for the eigenvectors of an n by n matrix. So then S and S to the 1/2 are also n by n, right? And so therefore us to the 1/2 is also n by n. So somehow this matrix is a little bit too big. I'm like, oh yeah, it looks like I have the solution, but first of all, that matrix is actually a little bit too big. Okay, so that is the first caveat, is that us square root may have too many columns. We got the right number of rows, but we might have too many columns. We only need d coordinates, and this is giving us n of them. Okay, so that's the first caveat, but the second caveat is that hx is only unique up to a linear isometry. And what I mean by that is some matrix R, so that R times its transpose is the identity matrix. So an example of this, examples are rotations, reflections. And so let's dig into that a little bit. So if I want to apply a linear isometry to hx, what I have to do actually, so normally, the convention is that or the convention I prefer and I'm used to, and I think most people do, is that when we're applying a linear operator, we're applying it to a column vector, and we multiply on the left by a matrix that's representing the linear operator. But in this case, I've stacked the points in hx up along the rows, so what that means is when I apply this operator, I actually have to multiply it on the right. Okay, so that's just one kind of annoying thing in this convention of putting the points along the rows. But anyway, okay, so that's going to apply the linear operator to every point in hx. So if I write down this equation, that's going to be hxr times hxr quantity transpose. And now if I generalize this rule that I've been using on the transpose and expand this, then this is going to be hxr times r transpose, x transpose, h transpose. Well, guess what? Didn't I just define by definition that this matrix R is linear isometry, and so therefore this is the identity matrix? And so I get rid of this, and this is the identity matrix, does nothing. I'm left with just hx times x transpose h transpose, which of course, as we already argued, is hx times quantity hx transpose. And so what I'm showing here is that, again, there could be actually many different matrices that satisfy this equation and lead to the exact same factorization here. And they will not necessarily be equal to hx, the thing I got when translating this to the origin. Okay, so, but they will be unique up to, we would say, up to this linear isometry. So I might get some rotated or reflected version back. All right, but neither of these are deal breakers. And so let's just proceed. We have enough for an algorithm now. So here it is. I'll write it in comments here. So CMDS algorithm. So given a distance matrix, D, here are the following steps. Step 1. Whoops, I accidentally entered there. Step 1 is compute the square of the distance matrix. Now we already have that. But we're not always going to have that. Sometimes we'll be given some other distance matrix that came from something else, and we got to remember to square it first. That's important. Step 2 is compute the double centering of this matrix. Okay, so I did that here. So maybe I'll call this C for doubly centered. Step 3, compute the eigenvalue decomposition to get the spectral factorization. So let me focus on that step now in code and have a look. So there's this method called np.linealg.eig, or Hermitian eigenvalue decomposition. Hermitian just means it's a generalization of a symmetric matrix. This can do better eigenvalue solvers that know, for example, that you can only have real eigenvalues. Actually, I'll show you the difference real quick. If I were just to do eig, okay, so the first thing it returns here are the eigenvalues. I know I'm going to put them along some matrix called S. And then it's going to return the eigenvectors, corresponding eigenvectors in columns of this matrix U. If I were just to do eig of C, let's print out the eigenvalues and look. So notice how they're complex numbers. That's a bit annoying, and actually kind of suggests that it's doing too much work because these are really tiny complex numbers in all cases. But if I switch to eig H, they're all real numbers. Okay. Now, I know that C is a Gram matrix, so I should be getting only non-negative eigenvalues. But for numerical reasons, I see they're very, very tiny negative numbers. So really, I should just clamp those at 0. In fact, I could see there's only 2 eigenvalues that are of note here. And they're the last 2. Actually, I did say, I did prefer those diagonal elements of S to be in decreasing order. So let me just go ahead actually and reverse this real quick. I'll also just clamp all the ones at 0 that are supposed to be 0. And let me also reverse U. So I'm going to take columns as they are, but I'm going to present those columns in reverse order. Okay. Nice. So that's it. We get the spectral factorization, and now step 4. Okay, so we'll just make sure the code runs. Step 4 is compute US square root to extract the coordinates that we're looking for. Now we have too many columns, but I'll just do it anyway. Let's see. So I'm going to call this matrix Y. That's going to be the matrix that is my output of this algorithm that I hope matches the geometry of X in this case. So that's going to be U dot, and actually S, it had given us back the eigenvalues as just a list, but mathematically I'd written this so that it's diagonal matrix. Okay, so I'll see here it's a diagonal matrix of square root of S. And supposedly this contains our coordinates. Now it contains a lot more than what we need, right? We only think we need 2 coordinates. We happen to know that this comes from a figure 8, so we should only need 2 coordinates. But it actually comes back with 101 coordinates because there's 101 points. Therefore, this matrix C was actually 101 by 101. But let's just look at this as an image. And we see, yeah, there's only 2 coordinates that really stand out. The coordinate in the first column, the coordinate in the second column. And of course, that should make sense because, we look at this equation, and what it's doing is just taking each column and multiplying it by the corresponding eigenvalue. So in fact, to write this a little more clearly, yeah, this is how I'd write it mathematically, but really, this is, if this S comes back as a list, I can write this simply as I'm scaling each column by its corresponding eigenvalue. All right, so each column has an eigenvector, and I'm going to scale it by the corresponding eigenvalue. So really, it's much faster just to write it like this, rather than putting it into a diagonal matrix. Oh, and let me not forget to take the square root. That's important. There. Okay. So I get the same thing. But I think this makes it a little bit clearer to see. Yes, you can see it in the matrix multiplication, but I think it makes it a little clearer to see that what we're doing is scaling the columns. And for any column that has 0, that means that it doesn't contribute at all. It's an irrelevant coordinate. It's like saying, hey, yeah, I measured this figure 8 with 2 coordinates of the Cartesian plane. I could also draw that figure 8 in 3 dimensions, but that third dimension would just be 0, right? I can certainly use the z-coordinate, but this z-coordinate would be 0 the whole way through. I could use a w-coordinate, but the w-coordinate would be 0 the whole way through. So somehow I only actually even need the 2 coordinates, is what I can see from this, just by looking at the eigenvalues. There's only 2 eigenvalues that really stand out, and the rest are basically 0. Okay? So let me just make a scatter plot of this. Let me pull my code from up here so I get the color map right. So let me make a scatter plot of this and see what it looks like. And let me not forget also to make the axes equal. So yeah, let's go ahead and plot this and see, did we actually get the coordinates back? All right, so there we go. Very cool. And when we look at this, we can see directly the second caveat here. Because it can be any rotation that comes back in these coordinates, any rotation or flip, what we end up with is the first coordinate is the most important one, or more precisely, the axis of greatest variation. And then the next axis will be the next most axis of variation. And here there's only 2, so it would just be whatever's left after you project away the first axis. So that's how the second caveat shakes out in purpose, and I'll prove that more formally in a moment. But now I think we can pretty much see what happens. I do just want to dive a little bit more into caveat 1 though, because what if I don't look at all of the dimensions that I get back? In other words, what if I have more than, in this case, 2 columns of view that are important here, that have non-zero eigenvalues? So that would happen, for example, if I made some kind of 3D shape and I asked you for, and I only looked at the first 2 axes. So let's do that. I'll make a helix here. So a spiral shape. Let's say the spiral shape goes through maybe 6 cycles. So if you go from 0 to 6 times 2 pi. And okay, so yeah, let's make this and 3. So we're going to have the sine, cosine actually first, then sine. And then we'll just put t directly in the third axis. So now we have a 3-dimensional thing. And if I get the square distance matrix of this and run the algorithm, what do I get? Okay, so what you notice here is the most important axis is actually the axis that goes up the helix. But then there's two more axes, and actually they're equal here because this is a circle. And so it just gives me one of them. But I don't really see the fact that it's a circle here when I plot it this way. So this is a form of linear dimension reduction. So in other words, if I look at the eigenvalues here, and I see that there's really 3 eigenvalues that are important, but I only take 2 of them, then I know I'm not going to perfectly capture the geometry of the distance matrix that I was given. But it ends up being the best that I can do in this framework with only 2 dimensions because I take the most important ones first. Okay. Alright, so I want to talk more formally about what's meant by an important direction here and why the most important directions come out first. So even though this figure 8 was rotated and the canonical factorization, the first axis was somehow the one with most variance. And so in order to do that, I'm going to take a brief detour into something called principal component analysis, or PCA, which is actually, you'll see, is really the same thing. But in the formulation of PCA, we're a little bit more upfront about what's meant by an important axis. So here I want to define something called projected variance onto a unit vector v. So this is defined for point cloud as the sum of the square dot products of every point with this direction vector v. So that is the definition there. And you notice what this does is it takes the dot product of every point in x, and even if that dot product is negative, this will come out to be a positive number. So no matter whether the point is to the right or to the left of the vector, this will come out positive if the projection is non-negative. So somehow this is recording how much do all the points agree with the line that goes through this direction. So I don't care about positive or negative direction, I can go in both directions. Now this is something that can be written very readily in matrix form. The way that I have x set up with each point in a row, and if I assume that the column vector, that v is a column vector here, I can write this as x times v. So that matrix multiplication is going to take all the dot products, right? So this will give me a column vector, that's n by 1. And then if I do the transpose of that and multiply it here, I get a single number, which is the sum of all dot products. So it's kind of funny because it's doing a bunch of dot products, creating a vector of all the dot products. So an n by 1 column matrix of n dot products. Then it's taking the dot product of that vector of all dot products with itself. So the dot product of dot products is how you would actually write this equation down. So let me call this matrix A for a second. And what we notice is, well, this is also a Gram matrix. And if I hone in specifically on the x part of it, so if I expand this transpose here, what I get is v transpose x transpose, applying our favorite rule again. And then if I do the associative rule, let me hone in on this part. Actually, I'm sorry, I don't want to call this A. I want to call this matrix in the middle here A. So I'll say, let A be this thing here. Okay, so we look at this, and this looks an awfully lot like the matrix that we were factorizing in multidimensional scaling, right? Ignoring the fact that it's not centered right now. But it's actually the other way around. So before we had x transpose, now we have x transpose x. So before, with multidimensional scaling, we were dealing with a matrix that was n by n, x transpose. Now we're going to deal with a matrix that's d by d. So x transpose x. Now let me do a factorization of this matrix. So I'll say, okay, let's do this factorization. Because it's a Gram matrix, I can do the same kind of factorization. In fact, I'm just going to use the fact that it's symmetric here. But so let me call the eigenvectors of this matrix v to distinguish them from the eigenvectors u that I was working with up here. But as we'll see in a moment, this is going to have the same eigenvalues. Okay, so the way that I would factorize this matrix, I would write it as v s v transpose. And so where I'm claiming that S are the same eigenvalues as you know, the factorization U S U transpose that I did before. And you know, sneak preview, I'll get to this in a second, but this is because it's really two different sides of the singular value decomposition of X itself. But let's just study this for a moment, this factorization. So what I'm saying here is, okay, I have, because this is a symmetric matrix, these matrices V, so it's orthogonally diagonalizable. So this matrix V has a bunch of eigenvectors along columns. So I'll say each vector column of V is orthogonal to all other columns. And yeah, it's a d-dimensional vector. So these, as opposed to the vectors we got back from classic multidimensional scaling, which had as many elements as there were points, these vectors have as many elements as there are dimensions. So we can actually view these vectors as direction vectors in the space, I guess I should say Euclidean space, which is, well, to be very formal, we'll say the reals in d dimensions. And so let's think about, okay, so what's the big deal about these direction vectors? Well, let's suppose we wanted to choose the axis of maximum variation that maximizes the projective variance. Okay, so let me take a second. I want to show you, if we just kind of looked around and tried directions of variance, I want to show you how this gives us a little magic trick. Okay, so I wrote a little bit of code here to make a random point cloud to show you what I'm talking about here. So this is some direction vector V that I chose here. And what I'm showing here is the projective variance, so simply summing up, doing exactly what I was doing. So summing up the squares of all the projections of the points onto this direction. So now I'm asking the question, okay, what do I do to maximize this projective variance? What direction should I choose? And of course I could just try a bunch of directions. Like, in fact, this is only in 2 dimensions, so I could parameterize this by just an angle around a circle and just try a bunch of things, maybe do a line search. But yeah, maybe I'll eyeball it. So I'm thinking here, okay, you know, this looks like maybe it's a diagonal. So let me try just a diagonal vector. I'll make sure it's normalized, by the way. I probably should have set that up here. So, oh, I think it did. I said, yeah, these are unit vectors. So let me just make sure that I divide that by its magnitude and make sure it's a unit vector. Okay, so I definitely got a better projective variance here. 8607. Okay, so when I was teaching this concept, I would often have my students compete and see what vector they could choose to try to maximize this. So can we do better? Well, maybe it looks like it's a little bit more vertical than it is horizontal there. So can I beat 8607? So I'll jot that down. Of course, we'd write this on the board. So maybe I want to make it a little bit more to the left. Okay, cool. So I did better. Is that it? Did I get it? Well, if I go back to this factorization, I can actually show that the eigenvector of this matrix with the greatest eigenvalue will maximize this. All right, so let's prove this. So what I'll do is I'll take the equation for projected variance here, and I'll substitute in the factorization that I've defined here. So I'll substitute in for x transpose x, this factorization. Okay, now I can write this factorization as a sum of individual projections of each column of V. So because the columns of V are orthogonal to each other, what I can do is rewrite this as just each column individually. So the action of this matrix is project onto each column individually, scale by the corresponding eigenvalue, and then multiply by the column over there. So in other words, it can be written as the outer product of each column with itself scaled by the singular, or by the eigenvalue here, and sum over all those. Okay, so this matrix VSV transpose can be written as this sum of rank 1 matrices. Now if I bring this on the inside here, so I do the opposite of distributing, so I put it back in, and then I write this here, I can see a little bit more clearly what's actually happening. So to see what the projected variance of a particular direction is, I project onto each column in turn. That actually gives me the cosine of the angle between V and this column, because these are unit vectors, so by the dot product rule, it's just going to be the cosine. And then I scale that up by whatever this eigenvalue is. Okay, so now let's consider taking V to be one of the columns. So because all these eigenvectors are orthogonal, that means that only the term corresponding to that column is going to be non-zero here. So this shows that if I take my V to be equal to one of the columns, then the projected variance is just Sj. So just the eigenvalue associated to that column. And so then it follows that making V be the first column will maximize the projected variance as that first eigenvalue there. So if I put all my eggs into the first column, then I will get, so assuming that these columns come out in a decreasing order of eigenvalue, just like they were with CMDS, then I'll maximize the variance. Because otherwise, if I don't align with the first column, then I'll get some component to the first column, but everything else that sums into it will be less. So it's like, I'm choosing some vector on the unit sphere in d dimensions, and if I move away from that axis with the largest eigenvalue, then my components along that axis can never be made up for by the components along the other axes. So anyway, this tells me that, yeah, it's the first column that I want if I'm trying to maximize projected variance. If I want the next most direction of maximum variance after that, it will be the second column. And if I wanted the third most direction of variance that's orthogonal to the first two, it would be the third column, and so on and so forth. So let's see, can I now win this competition? If I let this direction V here be the first column, then I get the projected variance 8768, which is greater than the one I had before. And if you're paying attention, you know that if I print out the corresponding eigenvalue, that is exactly the projected variance. So cool. Nice. So again, just the magic trick I can play with the eigenvectors of that matrix. Alright, so you notice here that I sneaked in the same letter for the eigenvalues of this factorization that I did for the eigenvalues of the other factorization. Now, of course, this one has a centered point cloud, but the argument that I'm making here applies to any point cloud, centered or not. So if you do, what I'm saying is if you compute the eigenvalues of x transpose, which is what we did for multidimensional scaling, and you compute the eigenvalues of x transpose x, they'll be the same. And that's just because all I'm doing here is the singular value decomposition. And so what I was saying is, okay, so I drew a little picture here of a point cloud with 5 points so I could really illustrate what I mean. If I were to line those 5 points up in a 5x2 matrix here, so 5 points Euclidean dimension 2, and take the singular value decomposition, well, the vectors that I get for classical multidimensional scaling are the left singular vectors. And then the singular values are the eigenvalues of that. And I end up taking the square root of them for the embedding. The right singular vectors are what we get from PCA. And then it's a little bit easier to see what's actually meant by the different columns here, how they maximize the variance. So let me just go through this really slowly and make sure it's totally clear. So I can eyeball this and kind of look at what the direction of maximum variance will be, and I can see that it's really this direction here probably. So let me call that direction V1 here. So that's V1. And then I can see that the direction orthogonal to that, that's the only other choice I have in 2 dimensions. In higher dimensions, this might be a little more interesting. But, okay, so those here are going to be the 2 directions that I'm working with. So V1 and V2. And those are going to go along the columns of V. So therefore, when I write it in this form, they're going to go along the rows of V transpose. Okay? So let me just get that down here. So what I'm saying is, the first row is going to be V1x, V1y. So it's going to be the coordinates of the first direction, the direction of maximum variance there. Then the second row is going to be V2x, V2y of V transpose here. Okay, so we line up the directions of maximum variance in decreasing order of variance. Then this matrix here is going to be, so the matrix of singular values is going to be the matrix of eigenvalues of either x transpose, or x transpose x. So I'm just kind of redefining, maybe reminding people how we define the singular value decomposition, because that's all I've done. I've done the singular value decomposition 2 different ways, but I have this really interesting geometric interpretation. And so then each column, whoops, I meant to make that as 2 there. Each column of U is then just going to be the projection of each point in X onto the direction corresponding to the associated row. All right, so in the singular value decomposition, we associate the columns of U with the columns of V, so therefore this first row here is going to be associated with the first column. And so I'll just write it out, I'll spare you. But maybe I'll do the first one just to show you, and then I'll include in the notes all of them. So this would be, the first column here, I'll just write it as P1. So for point 1, dot product with V1, V1. And then of course it's P2 dot V1, P3 dot V1, and so on and so forth. And then the second column is going to be P1 dot V2, and then P2 dot V2, P3 dot V2, and so on and so forth. So I might as well just finish. It's actually not that bad. P3 dot V2, P4 dot V1. Oh, I meant to say P5. P5 dot V1. So usually you should make code to do these kind of things when it's so repetitive, because it's highly prone to error. P5.V2. Okay. So anyway, this is what we get in the factorization here. So just understand that it's a singular value decomposition, and I think that makes it much easier to explain why these are going to occur this is going to be the most important axis first, then the second most important axis, and so on and so forth. Oh, and by the way, this also, I think, explains and shows a little more clearly why there's going to be so many 0 columns of U. If you're just taking the eigenvectors of x transpose, it's a square matrix that has as many rows as there are points. But we can see from this factorization that it's only rank 2, right? So it's going to have the rank of the number of singular values. So that's why we should expect a bunch of 0 eigenvalues. So that they're columns that don't actually contribute anything. Then the other thing I want to say is, look, if you just want the directions of greatest variance, for that reason, it's going to be a lot faster if you just compute the right singular vectors. So if the dimension is much smaller than the number of points, just compute the right singular vectors. The matrix x transpose x is much smaller than the matrix x transpose. But as we'll see in a moment, these don't always come from Euclidean point clouds where you can explicitly write that factorization as x transpose or x transpose x. Sometimes you've just given the distance matrix. It didn't come from a factorization like that, and so you've got to actually compute all the eigenvectors of a matrix that's the shape of the distance matrix. But if this is a Euclidean point cloud and you're computing the directions of greatest variance, definitely cut straight to the matrix x transpose x. So in this case, that would only be a 2x2 matrix. Even if there were 1,000,000 points in 2 dimensions, that would just be an eigenvector problem on a 2x2 matrix, which is extremely fast, and you can write it down closed form. with Kramer's rule. So anyway, that's just a small public service announcement about this. Okay, one more thing before I move on. So I walked away for a second and I realized I made a little mistake. These eigenvalues, S1 and S2, are what we got from the eigendecomposition of XS transpose and X transpose X. Those are the projected variants onto these axes. But actually, when this is presented in the singular value decomposition, these are actually the square root of those eigenvalues. And for a similar reason, I also have to normalize these columns. So these columns here are supposed to be unit vectors in 5 dimensions in this case. And so that's actually what they're going to be. And so this is why we had to multiply by the square root of the projected variance before, or the square root of these eigenvalues when we were doing the embedding in classic multidimensional scaling. So the square root of the projected variance is really like projected standard deviation, or really just the projected scale. This is directly the amount that I have to scale the vectors. So it's a scalar that I can apply to each of them, a global scalar, to get them to be the right magnitude in each column. Okay, so just wanted to mention that, make sure that was correct with the singular value decomposition. All right, so we're going to shift gears, but let me just quickly take the code that I wrote and encapsulate it in a nice way in a method. So here I'll write a method, I'll call it get CMDS. So I'll say get CMDS of some particular distance matrix D. And now I actually need to do that step 1 because I'm not necessarily going to be presented with a square distance matrix. Another thing I can do, I'll just show you here, this is a little bit inefficient because I end up, when I do the centering, I end up computing the mean of the vector over and over and over again. I actually only need to do it once. So what I'll do is I'll just take this square distance matrix. I'll first subtract off the mean of each column. So yeah, before it would just keep computing the mean of that column, and every time it had to subtract it off of an element. So here I'll just say s squared axis equals 0, keep dims equals true. So this is going to subtract off column means. And then this is going to, if I change that afterwards, so I take the result of that and I subtract off the row means. Subtract off row means from result. Then that's going to be more efficient. I just need to remember to still multiply this by -0.5. Okay. So that's going to be a little more efficient. And then I've already taken care of this other inefficiency that I had before, so I think that'll be good. Let's just make sure this method works. If I were to give the distance matrix, so I'll say D is equal to get dist match of X here. Let me make sure, things get a little bit mixed up in the cells here. Let me make sure that's actually the point cloud that I intended it to be. So I'll just copy and paste this down here real quick. So I'm going to test this out here. So that's X. And yeah, I actually want to now take the square root of that. I have a, so I'm not going to take it for granted that I'm presenting a square distance matrix here. I have a parameter to this distance matrix that does the whole square root thing, making sure it doesn't take the square root of negative numbers. So I'll say here square root equals true. And now let me try to call this method, get CMDS D. Hopefully that runs. And if I do the scatter of that, then I hope I get back this nice aligned figure 8. And I do. Okay, good. So now I got that figure 8 aligned with these canonical axes here. Beautiful. All right, so I think I have a method that's ready to go for any general distance matrix. So I can start to talk about non-Euclidean distance matrices and just go ahead and pass them along to this and have a look at the coordinates. Now, before I go any further, I do also have to issue a note of warning here. It will not be the case that I can perfectly reconstruct a non-Euclidean distance matrix using Euclidean coordinates. And if you know a little bit about geometry, that should make sense. I mean, if I'm in different metric spaces, they can't necessarily be embedded in any finite dimensional Euclidean space. So a note of warning, we shouldn't expect perfect reconstructions. I mean, already we talked about, even if we have a Euclidean point cloud, we're not necessarily going to present a perfect reconstruction because we might just not use all the coordinates. But sometimes, even if we use every single coordinate that we get back, we can't do a perfect job. Oh, and actually, I also just realized I should probably, just so I know a little bit more information, I should probably also return the eigenvalues here so that I can look at them and see. If it was Euclidean point cloud, I can see which ones are 0. If it's non-Euclidean point cloud, you'll see in a moment, some of these are going to be negative. Okay. Because I'm no longer going to be able to rely on the fact that I have a Gram matrix. It's not going to be a Gram matrix anymore. Okay. So I'm getting ahead of myself. Let me first just show a counterexample to this idea. All right, so the easiest counterexample I can think of is on the sphere. And so what I'm going to do is choose a point right in the center of the sphere here. And then I'll choose a point that is along the, so this is the equator here. Along this equator, this great circle that's 90 degrees over in that direction along the equator, and I'll choose another point that's 90 degrees in this direction along the equator, and then I'll choose a point that's up here that's 90 degrees from all three of them. It's on the top. And so what I'm going to do is fill in the distance matrix using a spherical distance, using, measuring along the curved surface here what the distances would be. Let me set, okay, actually I should give these points names. I'll call this one A, I'll call this one B, I'll call this one C, and I'll call this one D. Okay, let me set this sphere up so that it has a radius of 2 over pi, and the reason I'm going to do that is because if I know that the distance, the arc length from A to C, which would be the distance along this curve from A to C, that is an angle of pi there. So I know that the distance would be pi times the radius. Well, pi times 2 over pi is 2. Okay, so what that would do, that would shake out the distances so that the distance from A to C is 2. So I'll write that there. I could also go, actually there are 2 geodesics here that get me from A to C. I can either go this way along the front of the equator, I could go the other way along the back of the equator. Both of those paths are the shortest paths here that give me a distance of 2. By the way, that's already something different from Euclidean space, the idea that you could have 2 paths that are the shortest paths between 2 points. Anyway, okay, so that's 2. And then, if I'm going along only 90 degrees, that would be a distance of 1 there. And so, and by the same argument, this would be, all these 3 distances here would be, trying to draw this right here. So the distance from B to D would be 1, and then the distance from A to D and C to D would also be 1, right? So let me just fill in this table real quick over here. Okay, so there's the distance matrix, and I went ahead and copied it over into NumPy here. And actually, spoiler alert, I'm going to have to make a slight modification because this matrix turns out not to be a Gram matrix, or the square of this matrix is not a Gram matrix. And so some of these are going to be negative, but I want to actually know that. I want to take note of that. So I'm not just going to cut those off. What I'll do instead is just be sure to only compute the coordinates for these that are not negative, so that I don't have to worry about taking the square root of a negative number. Okay, so I might not return n different columns now of this y, but I do want to take note of what all of these are. Okay, so yeah, let's go ahead and get this here. So say ys equals get CMDS d, and let's look at that s. And so here I see, okay, I've got 2. This is my first eigenvalue. 0.5, 0 basically, and then negative 0.25 are my eigenvalues. So this centered version of the square distance matrix is not a Gram matrix because I have a negative eigenvalue. But it is still symmetric, and so I can still get these orthogonal columns, and I can still plot some coordinates if I want to. So let me plot the first 2 coordinates. So since those are the ones that are showing up here that seem like I can actually look at them. They correspond to non-negative and non-zero eigen values here. Actually, I don't need to print them. I'll just plot them. And so I look at this, and this looks a little bit like the picture that I drew here, right, with those 4 points. But if I look at the coordinates, I see something's a little bit off. So, the distance between the left point to the right point here is 2. So I see x coordinate -1, x coordinate 1, and they're at y 0. So that's 2. But this point in between them is supposed to have a distance of 1. And I see that it doesn't, because yes, it changes by 1 in x, but it also changes by 0.5 in y. In fact, let me emphasize that. Yeah, so this is a distance greater than 1 here. So we're seeing some distortion here. So in fact, if I go and if I go and try to run this again and say, hey, you told me you were giving me back points whose distance matrix would be this. Is it actually the distance matrix I gave you? So let's compute the distance matrix on the points that we got back here. And if I look at that, it's a little bit messy because of the real numbers here, but I say 0, 1.2, 2. Yeah, right. So this is what I was saying. The distance is not 1 anymore. So I was supposed to see 0, 1, 2, 1. But I have some number that's not 1 anymore. So that's my distortion. And actually, I could argue that was already an impossible task. Because if I think about what this is saying, okay, I'm trying to put this into a Euclidean space where the distance between points is along a straight line. And so if I have points A, B, and C that, where I have distance from A to B is 1, distance from B to C is 1, and distance from A to C is 2, what that's telling me is that really A, B, and C should be along the line segment, right? The only way to have 3 points where the distance from A and C is twice the distance from A to B and B to C. The only way to make that happen is to have them be along a line segment, right? It's like a degenerate triangle. So yeah, we could do that. That's going to give us a distance of 1 there, and that'll be distance of 1, and then we have a distance of 2. That's fine. But now I'm asking for a 4th point, D, which is equidistant from those 3 points, right? So D is supposed to be a distance of 1 from A, B, and C. And that's impossible. The only point that's equidistant from these 3 points on a line is a point at infinity, right? It's like saying, okay, you're telling me these points lie on a circle together, right? Because on the boundary of a circle, because they're equidistant from some other point, which would be the center of that circle. But these are along a flat. This is the degenerate circle. This is a circle with infinite radius. So the only way to construct a point that's equidistant from these 3 points is to put a point at infinity. And that's certainly not going to have a distance of 1, right? So that's some kind of contradiction there. By assuming that I could actually embed this in Euclidean space with straight line distances, it turns out to be impossible. Okay, so this is not possible in general, although this is not bad. We had a little bit of distortion, right? But it wasn't too bad. It just meant that some of these entries in the distance matrix of the points that we get are a little bit different from the distance matrix that we were given. But this still actually looks like a pretty good representation of what I drew on the sphere. Okay. So we can proceed. We just need to look at the eigenvalues that we get back and notice if some of them are negative, that means it can't be embedded in Euclidean space. That's what it means. So the Gram matrix, the centered squared distance matrix is a Gram matrix if and only if the points can be embedded in Euclidean space. All right, but let's proceed and try this on some of the applications. Okay, the first application is pretty simple. It's just a straightforward extension of what I did with synthetic data on the sphere, but now I'm using actual data that came from a survey of my students of what they thought the distance was between different academic subjects. And so I took this table and put it into NumPy here, along with a parallel array of the subjects are. So I can go ahead and run my code here. So I'll get the CMDS of this. Now, okay, let's actually look at a couple things. So if I look at the singular values here, I can see that the first dimension is very important. The second dimension, a lot less so, and then it really falls off. So it looks like I could capture most of the geometry in 4 dimensions. Actually, let's see how negative they are too. So yeah, actually this somehow seems like it could be almost Euclidean. This looks like it's almost a Gram matrix. So anyway, that's cool. I'll just look at the first 2 dimensions, so essentially I'm doing dimension reduction, even though it seems like I might really need 4 to faithfully represent it. But if I plot those first 2 dimensions, then I will see something like this. Actually, if I compare that to what I showed here, it looks like it's upside down, and maybe even flipped. So we'll see in a second, yeah. And so actually, the scale, the direction of these vectors that we get back is arbitrary. It doesn't change the projective variance if I flip the axis 180 degrees the other direction. So that's one caveat to be aware of here. I guess the library I was using years ago, probably in MATLAB or something, for whatever reason, shows a different flip of those eigenvectors. Okay, anyway, but let me just verify that, because let me put these subjects here as text labels, and I can do something really fancy here with Python looping. So I'll say for I, and then I'll say name xy, and enumerate zip subjects y. Ooh, this is super fancy Python here. Okay, so I'm doing a zip iterator to iterate through the subjects and the rows of this point cloud. So the first 2 columns there, I'm going to iterate through each row in parallel with the name of the subject. And then I'm going to unpack the name of the subject and each individual coordinate of that point like that. I guess I don't really need I there, do I? I guess I can just say, I don't need to enumerate, I can just say zip. Okay, that should be enough. So here I can say, okay, plt.text xy name. And there we go. So let's see, compared to the original picture I had years ago, put them right next to each other. Yeah, so it looks like I actually flipped this both left and right and top down. So both of the eigenvectors were flipped. But you see the same overall geometry, right? So this, they're still the same axes here. They just got presented in the flipped direction. So I like the way that my class kind of rated these, because they're like, well, CS and EC are very similar to each other, and then math is kind of the bridge between these subjects and philosophy. Or maybe you could say philosophy is the bridge between math and the humanities. So I thought that was kind of cool. Okay, so now I want to do this thing where I'm looking at people's ranked votings of different candidates and comparing them based on their choices. So going back to this class assignment I made, I had my students rank pop stars. Now, without loss of generality, I'm going to present their rankings as a permutation of the number 0 up to the number of choices minus 1. So here there are 8 choices, so this is going to be a permutation of the numbers 0 through 7 inclusive. So the number 2 actually refers to Dua Lipa. The number 7 actually refers to Journey here. But it's going to be easy to deal with these kind of permutations. Okay. So now what I'm going to do is try to compare 2 of these permutations and see how similar they are. And the way I'm going to do that is with something called the Kendall-Tau distance. And I have some notes on this here if you want to look at them, but the idea is actually pretty simple. What we want to do is count all the possible pairwise elections that the 2 raters disagree on. So in other words, if I take 2 of the candidates here, let's say 0 and 1, this rater is going to have 0 win, so 0 comes before 1. But this rater is actually going to have 1 win. 1 comes before 0. And so that is a discordant, called discordant pair. On some of them they agree though, they both put 4 before 3. They both put 1 before 2. But I want to count the number of pairwise elections that they disagree on. And that total number is what's referred to as the Kendall-Tau distance. Now I'm going to do part of this assignment. I don't want to spoil the whole thing, but let me do kind of the easy brute force way of computing the Kendall-Tau distance. This is just by enumerating all pairs and seeing how much they have in common. On the assignment, I had my students do a fancier version of this that uses merge sort, and I described this in the notes here if you're curious. You can actually do this in n log n time. But to keep it simple, let me actually just basically do it from the definition. So I'll enumerate all pairs in the first one, and then I'll enumerate all pairs in the second one and count how many are different. And so this is pretty easy to do with just creating a set of all pairs in the first one. So I'll say, let's make a little method here. Let's call it get Kendall Tau, and I'll say P1 for first permutation, P2 for the second permutation. And so I'll say, okay, maybe I'll call them pairs 1. I'm just going to make a set. So I'll say for I in range, let's just define a little variable here called n. That's the number of candidates. So for I in range n, and then for j in range I plus 1 n. So we're going to look at all possible pairs. I'll say pairs 1 dot add the tuple. It needs to be a tuple, so it's hashable. P1i, P1j. Okay, so that's all the pairs. Now what I want to do, so I'll say here, step 1 is enumerate and store all pairs, pairwise elections for first rater. Now the next step I want to do is actually go through and enumerate all pairwise elections for the second rater and check them against the first one. Okay. So what I'm going to do here is say, and now I can compute the distance. So I'll say if the pair P2i, P2j, if this particular pair is not in the first pairs, then I know that's a disagreement. So if I had, in this example, if I had 0, 4 in the first set, now I'm looking through the next one, and I end up creating the pair 4, 0. And I look and say, is that in the first set? No, I can't find it anywhere because it's the opposite in there. So I'll do that, and I'll say dist plus equals 1 in that case, and they'll just return the distance. This is a simple O then squared algorithm for computing. Another thing you could do is run insertion sort and count the number of swaps that insertion sort makes. That's another n squared algorithm for doing this. So yeah, run a variant of insertion sort to swap the elements in this until they agree with that one. Okay, but this one is very straightforward based on the definition. So let's start to play around with this. And in fact, I don't even need I don't need to know who the stars are. I just need to make sure that I have a consistent way of labeling them here. Yes. Okay, so let's go ahead and just compute this Kendall-Tau distance on all pairs here. So I'll say, let me get a list. So there's a dictionary here, so let me get a list of, I'll say, people equals list raters.keys. Just I'll choose some arbitrary order of them. So now let me make a distance matrix, which is, I'll say here n is the number of people. So this is an n by n distance matrix, and what I'll do is I'll say for I in range n, for j. To save computation, I'm only going to compute the upper triangular part because I know this will be symmetric. The distance between Hannah and Emily is the same as the distance between Emily and Hannah, so do that. I plus 1 n. Okay, so I'll say dij is equal to, so get Kendall-Tau of raters, people I, raters, people j. And then once I'm done, so this makes the upper triangular part, I'll add its transpose to itself, so repeat on the lower triangle. Okay, so let's see, I'm going to say, let's see, didn't like that, should have said pair, this is called pairs 1, okay. Okay, anyway, so it ran that, well, let's go ahead and get an embedding. So let's see, so if I say y(s) equals get CMDS d, then, well, let's go ahead again and look at, I guess I'll both print and plot this. Okay, so clearly this is not Euclidean. So actually, this is a metric, by the way. This is a proper metric. It satisfies the triangle inequality, symmetry, and the, you know, being 0 if and only if the two things are the same. But it is definitely not a Euclidean metric. You're getting a lot of negative eigenvalues here. And actually, even if I try to, you know, look at the non-zero or the non-negative eigenvalues here, I see quite a few before they drop off. But you know what? I'll just look at the first two dimensions. So I should definitely expect distortion just looking at the first two dimensions. All right. So let's go ahead. I'll keep that there maybe, and let's make a figure with both of these. Or I'll keep that there, and then I'll make another figure, and I'll say PL2.scatter y. So let's just look at the first two coordinates anyway. I know it's not going to be necessarily the best. But yeah, let me do, again, what I've done up here with the plotting. So I'm going to do something similar where I say, so here it's going to be people. Okay, so let's see. Did I get the same results that I got back here? So let's see. This is it for my class. Let's have a look at these side by side here. Okay, so again, it might be flipping things, although in this case, okay, I think it got it spot on. It got it exactly how I had it there. Because, well, it turns out I wrote the code for this assignment, so it's using the same libraries in NumPy and SciPy. Okay, cool. So now you can see, and just to do a spot check, a couple things here. So somehow, like, Camilla and Hannah should be pretty similar. Well, let's check that. If I look at the distance between Camilla and Hannah, so I'll say get Kendall Tau, Raiders Camilla, and Raiders Hannah. Whoops, I meant to spell, first of all, sorry Camilla, I spelled your name wrong. Camilla had a couple class issues, a great student. Hannah as well. This is a really solid class of students here. What did I do here? Oh, Hannah has a space. Okay. Okay, actually, that's interesting. So they were a distance of 16, which is actually not that close. So that might be an example of distortion. Let's look at Bev and Brady here instead. So, okay, we're definitely seeing some distortion here. Bev versus Brady. Okay, they're a little bit closer. Let's pick Zach and Tim. Zach and Tim. Okay, Zach and Tim are close. I think that's about as close as they can get. But there is a little bit of distortion in other places. But yeah, maybe let's take the extremes too. So Dante and Audrey here. Are they really far? So looking at Dante and Audrey. Once again, okay, Audrey has a space. Okay. Yeah, so they're far. Actually, it's helpful to think, what is the maximum Kendall Tau distance? In other words, what's the diameter here of this point set? And that should be n choose 2, or n times n minus 1 over 2. Oh, whoops, yeah, where n is the number of candidates here. So n is actually 8. Okay, so 28 is the most number of pairwise elections I could possibly agree on if one of these is the complete reverse of the other one. So if I look at Dante and I look at Audrey, so here's Dante and then Audrey, they should be almost the reverse of each other. Okay, yeah, they are, except for, okay, if I reverse Dante, I'll print out Dante and then I'll print out the reverse of Dante. So the reverse of Dante almost agrees with Audrey, except looks like 0 and 2 got flipped in the reverse, and 5 and 6 got flipped. So there you go. That's why the distance is 26. They agree on only 2 things. They disagree on everything else. So I told them in class, hey, unless you want to really expand your horizons, the two of you probably don't want to go out to the movies together. Or to see a show together. A different yards of movies. Okay. All right, good. So I just wanted to show, this works all right, but there is a little bit of distortion. But it still kind of gets the extremities, and a couple of the close things are reasonable. All right, one more application of classic multidimensional scaling I want to do before moving on to p-stress. So remember at the beginning I said we're going to look at this canonical representation of 3D shapes so that if we move them around non-rigidly, so we've got this shape of 3D shape of a person, if they move their arms around, somehow it won't matter, we'll always get the same shape. And the way we do that is by using a distance not by a straight line distance, but something instead called a geodesic distance. So I had a lab where I had my students do this in my data structures class. I said ordinarily you would use a straight line distance to measure the distance like between these two fingertips, and so in that case you'd be able to leave the surface. So I said that's as the bird flies. The bird flying shortest path would be that. But for a geodesic distance you have to stay along the surface. So that would be as the ant crawls. And so the idea here is even if the fingers move around, the path that the ant sees is intrinsic, so it's going to stay along the surface. It doesn't really realize that the fingers have moved around. So this distance won't change even if there are non-rigid motions, whereas this distance will. So what we'll do is we'll try to get this distance and then reconstruct a Euclidean point cloud that realizes that distance as best as possible. So this is kind of like a generalization of the sphere example I showed at the very beginning of these non-Euclidean examples. So in the sphere I was measuring the distance along a geodesic shortest path on the sphere too, just to go back and show that again. You know, there was a shortest path along the surface there of the sphere. I couldn't cut through the surface or leave the surface. I had to follow this. So this is really a generalization of that. Now I can do this on any shape. I should point out though that Dijkstra's algorithm is actually not the best algorithm to use for this. It was what I happened to be teaching data structure, so I used it at the time. But in general, you actually want to be able to cut through triangles on the surface. So this is a mesh that I'm going to look at in a second of a person. So I'm going to go and look at this person in different poses, moving his arms around. So yeah, it's made up of vertices and triangles. And if I'm going to use Dijkstra's algorithm, those you're familiar with it, as shortest path along a graph, you can only follow these edges. But the shortest path that the ant would crawl sometimes will cut through triangles, so we need a more sophisticated algorithm. And there's a generalization of Dijkstra's called fast marching algorithm for this case. But actually even more practical than that is something called the heat method by Keenan Crane and others. And so I'll link to something that explains this more. It's a really cool method. Maybe I'll make a video on it someday, but for now we're going to take it for granted. We're just going to say we have some kind of algorithm that can measure the distance from a point on the surface to all other points on the surface as the ant crawls, possibly cutting through triangles on the discrete representation of that surface. Okay, so going back to the code here, I've imported some things that are going to help me deal with 3D shapes, including a library by one of Keenan Crane's students that implements this heat method. So what I can do is say solver equals pp3d, that library, dot mesh, mesh heat method distance solver. I'm going to pass along the vertices of this mesh and the faces of the mesh, which I actually loaded with a little code that I wrote here. I'll provide that. Okay, so I do that, and then I want to compute the distances for all vertices along the surface. And so I'll make a distance matrix that can hold n by n there. And let me loop through. This is going to take a second, so I'll feed this range iterator to tquadum library. That'll have a progress bar. And then there's this method in the solver called compute distance. And I just give it an index, and that's going to return an entire vector. That's a really cool thing about this method. Actually, from a single point, you get the distances to every other point when you solve this. And so I'll just put those along one of the rows, the ith row, or ith column. This thing is symmetric, but I'll put this along the ith row there. Okay, so this is going to compute the distances. And then when I'm done, I'll do classic multidimensional scaling. The only thing is, this is a big matrix, so it would take a long time to compute all of its eigenvectors. So I'm not going to do that. Instead, I'm going to only compute a few of its eigenvectors, which means I should make a modification to this method here. Instead of using NumPy's linear algebra, I'm going to use SciPy's linear algebra, because SciPy's linear algebra has a special version of Eig that allows you to only compute the largest eigenvalues if you want. So if I say scipy.linealg.Eig, I'll look at the documentation here. There's this parameter subset by index here. And if I look at that, it says this two-element iterable defines a start and end of the desired eigenvalues. So if I wanted the largest three eigenvalues, I would do n minus 3 to n minus 1. So I guess what I'll do here is I'll say, let me add a parameter to this method called k. And I'll say, okay, this, so get CMDS of a distance matrix. D is the distance matrix. But this parameter k, I'll say this is the number of largest eigenvalues we want. Or -1 if we want them all. Okay, so that'll be the convention here. So I'll say, yeah, if k is -1, I'll just use NumPy's version, so compute them all. But otherwise, I'll compute the k largest. And so looking at the documentation here, that would be, and let me throw this up at the top here so I don't forget it. Let's just import scipy. And yes, I want to say, okay, subset by index. I'll say su equals scipy.linealg.Eig c subset by index n minus k n minus 1. That should do it. So, okay. Yeah, let me just try to run this. I'll still have to reverse them, so that should all be okay here. So I'm going to say here y s equals get CMDS this distance matrix D, and I'm going to pass along a k. We're going to look at this in 3 dimensions, so I'll give it a k of 3. And this might still take a second because it's a really big matrix, but it was going to take forever if I did it otherwise. But I'll stop recording this video for a second just to let it run. Okay, so I went ahead and I ran this actually both on this 91 shape and also on this 99 shape. So here's the 91 shape and here's the 99 shape. And the idea is, even though he's holding his hands up, somehow the distance from the fingertip to all the other points here should be the same if I'm forced to say along the surface. And so if I use those distances on both shapes, then the classic multidimensional scaling version should be the same or much more similar on both of them than this here, and they should line up much better. So if I plot the results all on top of each other, what we get is this monstrosity here. So 91 is in magenta here. Let's just look at that actually. So 91, let me turn off 99. Okay, so the original is there, and then the canonical version is looks like this. And if you look at it, it kind of makes sense because you see, okay, what we're trying to do is come up with a straight line distance that best matches the geodesic distance. Well, the tip of this toe is very far from the tip of the other toe because I have to walk all the way along here. And I see a similar thing happening with the arms, right? So I have to walk all the way up this arm and then all the way down the other one to get between those two fingertips. And so you can convince yourself that this is kind of what it should look like. These extremities should be like almost at the vertices of a tetrahedron around this thing. And in fact, if I look back at the paper, that's pretty much what they got. In the lower right here, you see that sort of figure. And the really cool thing here again is that if I look at the same thing on the other shape, so there's the other shape. Whoop, let me get this back here. Okay, yeah. So even though he had his arms in a totally different place, this other shape came out looking pretty similar. Now the geometry might be a little different between these two, or something might have happened. You know, they're just not lined up perfectly, I think. Oh yeah, it looks like maybe just a translation. Oh, they're not quite. I guess I'd have to move this up. But anyway, they do line up much better. So if I were trying to match like fingertip to fingertip, I could do a much better job in this representation than in the other one. Okay, so I thought that was kind of cool. And you can see it's actually not, if you leverage these other libraries, not a whole lot of code to do that. Maybe in a future video I'll talk about how this actually works under the hood. But for now, we can take it for granted. Okay. Okay, I'm finally ready to go over a different kind of multidimensional scaling called p-stress. It's different from classic multidimensional scaling. And so the biggest difference is we're going to choose up front how many dimensions we're able to use and make the best use of those dimensions. As opposed to before, where we might end up with a lot more dimensions than we actually take because we're factorizing this n by n matrix. So here, I had 30 dimensions, but I only used 2 of them. But if I told you up front that I was only going to use 2, well, maybe you could do a better job because you didn't have these other ones to play with. So that's the biggest difference here. It also uses a slightly different objective function. But let me be a little more precise here, and I'll write it down, and hopefully that'll make more sense. So I'll say given an n by n distance matrix, D, and n points in k Euclidean dimensions, of the p stress of, let me call these x. I'll say n points x in k Euclidean dimensions. The p stress of x with respect to D is written as follows. So what I'm going to do is look at the discrepancy between the distances, the pairwise distances in x, between what the pairwise distances should be according to D. So I'll look at all pairs of distances, and I'll look at the difference between what that distance is supposed to be and what it actually is. So I'll say this is the distance between point xi and point j, xj. And so I'll raise that to the pth power for p stress, and then I'll take the pth root of that. Okay, so do my right parentheses here, and there we go. Okay, so that is the definition of p stress. So I'm summing up over. Oh, sorry, that one over p should go on the outside. Okay, there we go. All right. So yeah, I'm summing up the discrepancies in the distances. It's like a distance of distances, a distance between all pairs of distances. So yeah, you could view it that way. You could view it as the p, the distance in the p metric between all pairwise distances it's supposed to be and the pairwise distances that you actually have with these points in x. Now usually people use the 2 stress. And so that, sometimes people just call this the stress, and so that would just be this squared to the 1/2, or otherwise known as the square root. So I'm actually going to use this most of the time. The 2 stress, that's usually what people refer to as. So yeah, this is actually just kind of like the straight line distance between the distance, if you were to flatten this distance matrix out, and then you were to compute a distance matrix on the fly between these points, and you flatten them, it would actually be the straight line distance between those viewed as distance matrices. Okay, but anyway, the important thing to notice is if these points actually are the distance apart that they should be, this difference here will be 0. Okay? Now, so again, the cool thing about this is I could choose what I want k to be ahead of time and try to make the best use of those dimensions. The problem is it's a little bit harder to solve than classic multidimensional scaling. I can't just do a simple eigendecomposition. I'm going to have to use some other kind of iterative numerical algorithm. Now, if I look at this paper here, where they talked about the bending and variance stuff, they were able to solve this using something called smack-off, this higher order optimization technique. But I'm going to be a little bit lazy here, and I'm going to solve this just using gradient descent in Torch, because I can code it up and it will be easier to explain. So let me do that. And so what I'm going to do is, okay, I'm going to import Torch here, and let me see if I can reconstruct the figure 8. So if I go back here and I create this figure 8, and I get its distance matrix, then can I reconstruct it from its distance matrix? So I'll say D, and now I'm not going to work with a square distance matrix, I'm just going to work with the distance matrix straight up. I'll say get dismatch x square root equals true. I'm actually going to take the square root of the squared distances there. So from that matrix, can I reconstruct it? So here's what I'm going to do. Let me copy this over to Torch, to a Torch tensor. Let me also now make, so I'll say n is equal to d dot shape 0. Let me randomly initialize. So one of the dangers of gradient descent, it's very sensitive to initial conditions, but I'll start by randomly initializing these coordinates of the endpoints in k dimensions. And we'll use gradient descent to refine them based on this objective function. So you'll say x is equal to torch.rand, I'll say n2. All right, so they start off random. And actually, the other thing I'm going to do here is I'm going to say dot requires grad. So what I'm going to do, I'm optimizing over these coordinates. Those are the variables that I have to play with, the coordinates of all these points in the point cloud x. So those are the ones I'm going to be taking the gradient of the objective function with respect to those and doing gradient descent. And so what I have to do is make an optimizer, and I'll just use Atom. Why not? We'll see how this works. I don't know. And then I'll say the learning rate, the magic number that I've heard about. Whoops, I meant to say torch.optim.atom. Let's see, did I spell this wrong? It's supposed to be capital? Yes, okay. All right, good. So we have this optimizer. So now let's try to do, set up this objective function for some number of iterations. Maybe I'll say 100. I'll keep track of what the loss is over time, make sure I'm actually getting better. And what I'll do here is I'll go through, so I'll say for I in PPDM range and iters. Okay, so first I have to zero out, should be 0 grad, right? Let me just check that. Wait, optimizer. Oop, I spelled it wrong. Okay, I'm like, good, I thought I knew what I was doing. Okay, yeah, so first I need to clear the gradient. Then what I need to do is compute this loss function. So what I'll do at each iteration, I'll say, you know, this distance matrix that I'm getting at this iteration, it's going to be, so I'm going to do the same kind of thing I did before to compute the distance matrix. Let me go back up to that method. I'm just going to write this in Torch language instead. So basically the same thing, except instead of torch, mp.sum, it's going to be torch.sum, and instead of axis, it's going to be dim. Otherwise, it should be the same. So let me just make sure that that is true. Oh, and also, okay, torch is very general with the tensor, so there's not a dot method. I think I have to say torch.matmul x. Hopefully the transpose works here. Let's see. Okay. So maybe real quick, let me just check this versus. Okay, DSQR. I mean, it's going to look like noise. It's going to look like crap. Oh, it's okay. I've got to take this out of gradient mode. So I'll say dot detach. Okay, this is going to look like crap, but let me just compare this to make sure that I'm getting the same thing as I get when I call this method with NumPy. So get this match. So this is the square distance matrix right now. Let's just check that. NumPy. Okay, good. They look like they're the same. Okay, yeah, so good. So I'm doing the same thing in Torch, but I'm doing it in Torch with respect to this differentiable thing. So now anything I do on this, I can take a gradient of it with respect to the variable x. Okay. All right, so one thing I need to be a little bit careful about here is I am actually going to be taking the square root of this distance matrix here. So let me make sure that I'll say anything less than epsilon is equal to 0. So I'll make this some small number. Because actually, the other thing is I'm going to be taking the derivative of this, so I need to watch out because the derivative of the square root is 1 over 2 times the square root. So the square root's going to end up in the denominator. So I definitely don't want, even really tiny numbers, I don't really want those to be in the denominator because they're going to blow up the gradient of the square root. Okay, All right, so let's just try to implement this equation now. So I'll look at what is the distance between this and the original distance matrix there. So yeah, let me actually come up with a new name for this. I'll call this di there. So that's my di. And my objective function is going to be the sum of the squared differences between d and di. And I guess that better also, that epsilon that I have here, let me double check that method, make sure I'm being consistent here. Okay, yes, I better pass along that same epsilon to this method. Okay, so we got the loss there. And so I'll say losses, I equals loss dot value. Okay, now what I need to do is say loss dot backwards, and then optimizer dot step. Okay, so we're going to actually, this is going to do back propagation, figure out derivatives of loss with respect to each x coordinate, and this is going to actually take a step against the gradient. So, okay, let's see. Oops, I'm so used to using NumPy. I meant to say torch. Okay, let me just run this all again. Oh, I meant to say loss.item. Okay, yeah, this is... Okay, and is it backward? Okay, there we go. Wait, did this actually do anything? That seemed too fast. Let's look at the losses. Oh no, they did go down. Okay, so I don't know. Okay, so let's have a look. Wow, that was very fast. So let's see if we can have a look at what this actually looks like. So I'll say x equals x dot detach dot numpy. And I'll say plt dot scatter x 0 x 1. Okay, so looks like we have a little ways to go. Probably 100 iterations is not enough. Let's try 1,000. So yeah, I got to start over here. Okay. All right. I just need a lot more iterations. Maybe a bigger step size. So maybe I'll try a step size that's bigger here. And okay, well, it's still working itself out. Let's make sure the loss is actually still going down. Okay, it looks like the loss kind of saturates. So this didn't totally look like the figure 8. I'm going to play with this for a second and see if I can get a little closer. All right, so I was making a little mistake here because in this equation I'm supposed to be using the straight line distance. I forgot to take the square root. You know, I diligently made sure I wasn't going to take the square root of a small number, but I forgot to actually take the square root. So I'll see here, torch square root. And technically I should also be raising this whole thing to the 1/2 power. I should be taking the square root of the whole thing. I don't think that'll make as much of a difference, but this was definitely a huge thing. I was comparing the square distance to the square root distance and just getting the totally wrong shape. So now when I run this again and I look at the result, there we go, I get a nice figure 8 there. And if I look at the loss curve, I can see it goes down pretty dramatically. And I know I should be able to do this perfectly because I got this curve from 2 dimensions, so I should be able to do it in 2 dimensions, so the loss should be 0. It gets down pretty low. If I kept going, it should probably get even lower, but I'm happy with that. So just to show you though, if I run it again, it comes out in a slightly different rotation. It just depends on the initial conditions. It depends on the initial points that I chose. There are infinitely many solutions to this that would minimize it. Okay, but actually, I think a more interesting example would be one that I know I probably can't embed perfectly, or certainly can embed perfectly in Euclidean space, like the radars here. And one where I had a lot of distortion because, you know, I used maybe more coordinates than I was actually going to visualize. So if I insist up front on using 2 coordinates, can I do better? So I want to do that example. Let me just take this code real quick and encapsulate it in a method because I'm going to use this over and over again. So yeah, let me up to here. So I'll make a method here. I'll call it get p stress embedding. Okay, let's see. So we need to pass along here this distance matrix, and we also need to pass along. I'll say stress because I'm always going to do 2 stress, but yeah, I also need to pass along k, how many coordinates I want to use, I'll make that a variable. So, and let's see, yeah, I guess I'll pass along the number of iterations, and then the step size. So, yeah, so those are some things that I might want to change here. I don't think anything else in this changes. Okay, and so then, yeah, when I'm done, I'll just return x.detach.numpy. Okay, yeah, so we got here the D. So this is the distance matrix. K is the number of coordinates I want. And then, you know, editors and learning rate are self-explanatory there. Okay, let me just make sure I can still run that. So get stress embedding. So I'll say y equals get stress embedding of D using 2 dimensions with this epsilon and a learning rate of oh yeah, okay, I had an epsilon too. I guess I'll just fix that. I'll make that the last parameter. Okay, so it's supposed to be number of iterations. I use 1,000, and then go say x. Okay. Takes 4 position. I got to run that again. Okay, there we go. So does this work? Yes. Okay, good. And again, let me run it. I should probably get a slightly different answer. Okay, yeah. Anyway, I get different answers. All right. So now let me do this. So that was the figure 8 example. Let's do this on the rating data. So I'm going to go back up here and copy this code down again. And yeah, let me just get that all organized and I'll show you in a second. All right, so I ran it here. Actually, before I get too excited though, let me look at the losses. So I actually just a moment ago added, I'm now returning the losses as well to make sure this is actually converged. So if I plot the losses over time, okay, because see this hasn't bottomed out yet. So it's down at a loss of about 150. Let's see if we can get a little lower. So I will go for 10,000 iterations here and we'll see what the loss curve looks like. Okay, so this seems like it bottomed out. So it got at a loss below 100. Yes, so let's look now. So let's see a couple things here. I remember that Dante and Audrey are supposed to be really far apart, and I still see that. Remember before though, Camilla and Hannah looked like they were close together, but they actually weren't. So let's see, does that do better here? So Camilla, and where is Hannah? There's Hannah. Okay, so Hannah's a little far. So what about, so that's good, that seems a little better. If I recall correctly, they were Kendall Tau distance of like 16 or something. So if I get Kendall Tau distance between Raiders Camilla and Raiders Hannah with the space. Okay, yeah, it's 16. Okay, yeah, so that's actually pretty big. So good, they weren't too close together. And I can see here, does that look like it's almost 16? I can actually measure based on these coordinates. Okay. Whereas, let's see, Julian and Pat M should actually be pretty close together. So let's see, Pat M. Whoop. At one point I had a class with 3 Pats in it. I don't know if it was this one. Okay, good. Yeah. So this is actually looking a lot better. And let's just check one more. Connor and Tyler, they should be close. Okay, yeah, so that's one thing that's really, really nice about this distance. Now, if I look at this bending paper again, they seem to indicate that you can get a slightly better result that kind of preserves the volume a little bit more if you do this stress-based version instead of the classic version. So let me see if that's true for that example as well. So maybe I'll take D99 here, and yeah, so let me copy some of this code, and let me do, so I'm going to get the stress. This, yeah, I might need to adjust the parameters a little bit, but yeah, let me try this on D99 here. Maybe I'll put the number of iterations lower because there's a lot more points here. Okay, yeah, this is gonna take a little while. So let me run this. Okay, actually, I changed this code so that it's going to use the GPU, so it's going to be significantly faster. at this distance matrix on the GPU, make sure I was putting these coordinates on the GPU. And then I have to say one extra thing here, detach CPU numpy. Okay. Then it only took a minute. That wasn't too bad, or 30 seconds even. And when I look at the results, it's actually pretty good. So it's showing it in yellow here. See, it actually was able to retain a little more of the volume. So that looks a little more like the figures they were showing in the paper. And actually the head seems a lot better too. Like, it makes sense that the head should be like far from everything else out in this direction. Oh, one thing I forgot to do though is I didn't actually look at the loss curve here. So let's just see how it did. Okay, yeah, so it bottomed out. So yeah, we got there. Okay, so it seems to be improving on these applications, although, you know, the optimization pipeline is a little bit more complicated and a little bit slower. But there is actually another advantage I want to show to this. You can easily modify the objective function in a couple different ways that is more difficult to do with classic multidimensional scaling. So first, I'm going to introduce something called anchor points to this equation. So this is going to be choosing certain points to go to certain locations. And so what I'll do is I'll just modify the objective function to say, okay, the objective function is going to have the same two-stress that it did before, but I'm also going to add to it j anchor points. So I'll say lambda j. And what I'm going to say is that or I guess not j anchor points, but a set of anchor points indexed by j here. And j is going to refer to the point that I want to go after. So I'm going to say I want point xj to be as close as possible to some point. I'll choose the coordinates. I'll call them aj there. Oops, I don't want that all to be under square root there. What I want is, this is actually on the outside here. Okay. So what I'm going to do is fix certain points xj to be these vectors that I call aj. And I'll say that is, you know, part of the objective function, and these can have different weights. I'll call them lambda j here. So I just need to choose what indices that I'm doing and where they should be. So probably easiest if I start with the figure 8 again. And actually I should also, yeah, let me modify this method first to correspond to the definition that I had here. So let's pass along a set of anchors. So maybe before the number of iterations, let me pass along an array of anchors. And anchors is going to be an array of lists, or a list of lists of, I guess I'll put lambda first, I'll put the index j, and then I'll put aj. So this is going to be the anchors to include. And so what I'll do is, at every iteration, I will loop through the anchors. So I'll unpack this stuff. So after computing the first part of the loss, which is going to remain the same, I still want to preserve the distance matrix as well as possible. I'm going to iterate through, oh, I shouldn't call these, I should call this lamj, because lambda already refers to something else in Python. I'll say for those in the anchors, let's compute the distance first. So I'll say that is going to be equal to torch.sum, we'll say x at index j minus torch.from numpy aj.to device. Okay, so we're gonna take the difference between the two, the vector difference. We're gonna square that. We're gonna sum that up. And then if this happens to be bigger than epsilon, then it actually is contributing something. Then we need to look at it and add it to the loss function. We'll say that. So you'll say loss plus equals lambda j times the square root of this distance. And I think that's all I need to do here. Okay, so now when I call this, maybe I should make the anchors. Actually, I want this to be backwards compatible with the code that I already wrote. So let me make the anchors be the parameter after all this, after the learning rate. So this will be like an optional parameter that you can include if you want. I'll make it the empty list to begin with. But yeah, if you specify these anchors, it's going to add them to the loss function. Okay, so yeah, let's try to do this for the figure 8 example. So yeah, let me grab the figure 8 code again, and we'll just copy this down here. Do this again. Okay, I'll clean up that code later, but let's get to the anchors down here. All right, so I make this thing, and then now I want to make some anchors. Okay, first, before I do that, let me actually just plot where the original point cloud is, so I can see where I might want to put different points. Okay, so here it is, and so this has 101 points, and it starts here, and then it goes like this. So this is about 50 points into it. So maybe I'll say, okay, point 50, I want to anchor at x coordinate -10, y coordinate 0. So see if that moves this to the left. Yes, let me define my anchors here. So I'm not really sure what the lambda should be yet, but I'll just start off as 1 and see what happens. So yeah, I'm saying point in index 50, let's have that show up at location -10, 0. And see if that happens when I do the loss now. So I'll say eps equals eps, earth equals anchors. Okay, so that ran. Actually, let me scatter this. And actually, the other thing I'll do here is let me plot where the anchors are. So I'll say for lam j aj in anchors. Let's actually plot the location of the anchor. Yeah, okay, good. And maybe I'll make them all orange. Okay, so it was supposed to show up there, it didn't show up there. So maybe I need to increase the lambda here. So let me dial this up to 10 to make it a little more important. So let's see if that had an impact yet. Okay, it looked like one of the points started to move over there. I'm wondering if, yeah, I probably need to do more iterations. So if I look at the losses, okay, yeah, it's not done yet. So it was in the process of moving over there. Actually, give me a second. I'm going to make a little animation to really see how this is progressing. Okay, so check this out. This is pretty cool. So, you know, we start off with some random points, right? And then as we progress through the iterations, eventually they take shape. So the part of the loss function that's dealing with the p-stress is doing pretty well. But we still got to deal with this anchor here. So that other part of the loss that says, hey, this point here needs to end up there. At the same time, it still needs to preserve the p-stress. So this point is like contributing a lot to the stress. Its distances to all the other points are pretty far away. So as it moves this over here, it actually has to reckon with the p-stress too. So eventually the whole thing chases it over. And there we go. So we end up being able to move the shape over there and specify that, hey, that's where we want it to be. You know, the really cool thing here is we end up at the end with a loss of 13.37, if you saw that, which is LEET, right? LEET, L-E-E-T, like LEET code, right? When I was in high school, that was a big deal, L-E-E-T. Okay, anyway, so let me do this again, but let me add another anchor. So I had that anchor there for the 50th point at -10, 0. Let me put an anchor. So okay, I got to plot this again just to get my bearings. Let's put an anchor. So I know this has 101 points. Let's try to actually move the 0th point over. So we'll see if we can stretch it out a little bit if that happens. So this thing is actually 8 units wide. So what if I put the first thing at -10 and the one on the right here at 0? So see if I can stretch it out a little bit. So I'll add another anchor here, which is at point index 0. Yeah, I'll still include a lambda of 10, but I want this to end up at 0, 0. Yeah, let's see what happens. Okay, so I'll show you this real time as it's generating the animation here. So again, starts off with the random points. Now you can see there's 2 anchors though that I need to match. Let's see how it does. Okay, so it needs to have one on one side and one on the other side, and actually it can't quite reconcile those two. It sort of ends up in a position where it's actually happy to just keep those 2 points there, and it's like, it's close enough to the rest of them. What if we make that a little bit less important? What if we turn the lambda down a little bit to 1 instead of 10? Say, hey, you know what? I'm okay if you don't match those exact constraints at those points. So I'll dial that down a little bit, see if it does any better here. Or, yeah, what's it doing? Is it just going to give up? So that's interesting. Or no, okay, it's like rotating around. Okay, so I don't think it was done. I should have kept going. Yeah, let's run that again, maybe for 40,000 iterations. And also the initial condition is going to affect it too, so I should expect slightly different behavior each time. So yeah, it's a little bit different this time, based on the initialization. But now it looks like it's settled in a local min where it only satisfied the right anchor. So that's kind of interesting. So another thing we can do, actually, is say, hey, you know what? I don't necessarily care about preserving all the distances. I only need to preserve the distances that are between points that are close to each other. So I can look at what the nearest neighbors are, or just say, hey, I only care about preserving distances in this distance matrix that are under a certain amount. So I can create a mask. So if I look at this, I'll say maybe mask equals d less than 0.2. And compared to, so looking at this, so yeah, this is the original distance matrix, but I'm saying, hey, I just want to constrain probably a little more than that. So here's that pinch point, if you remember. So yeah, I definitely want to, at the pinch point, make sure that it still pinches there. But otherwise, I really only care about the points that are very close to you in the sequence. So yeah, let's do that. And I'll make sure this is a floating point type here. So yeah, let's make that mask there. And say, I'm going to ignore the distances that are in black here. I'm only going to actually include these yellow pixels in the stress computation. See, and then see if it lets it stretch out then, because I could still remain close to my neighbors while making this thinner and stretching it out. So let's see if that can happen. So I'll do this. Now I have to pass along a mask with this. So now I'm not backwards compatible anymore, but just bear with me. I'm going to pass this mask along here, and then I'm going to say mask equals torch.from numpy mask.to device. You can see I add a little bit of code here for plotting, but other than that, the only change I need to make here is in this computation here, I'm going to multiply this by the mask. So I'm going to say mask, and I'm only going to mask out the square distances I actually care about, the ones for neighbors that are close by. So let's see if that helps us out at all here. So now I'm going to go back and look again as this progresses, and I see, okay, I can see already, see the thing is it's allowed to stretch out. Ah, there we go. Okay. So it still kind of looks like the figure eight, although I guess it had one extra twist there. It was allowed to stretch out this time. Okay, so just to be clear here, this is the extra term that would go in this equation here. So this mask, I mean, technically could be a real number, but I was just treating it as a binary matrix here. So you either include the distance or you don't. And so there's a lot of flexibility there. It's very cool. And related to this stress tends to be a little bit better at dealing with outliers than the original classic multidimensional scaling. Okay. But yeah, let me try to do the same kind of thing on the 3D shape, and that'll be the last thing I do here. So looking at this 3D shape here, I'll see if I can get him to raise his arm. So kind of doing a non-rigid motion like I was doing with the figure 8. So I want to move one of his fingers up, but I don't necessarily want to move, I don't need to worry about if this finger is close to this finger anymore. I only need to worry about the finger being close to the things that are close to it along the surface. So it's okay if this finger moves far away from that one, but I do want to move it up. So let's see. So here I'm saying, okay, vertex 2, 4, 5, 0. I want that y coordinate to go up to about 0.8. Okay, vertex 2, 4, 5, 0. I want the y coordinate to go up to 0.8. So what I guess I'll do here is I'll say, okay, so the anchor is, right, okay, so first I say lambda. I'm not sure what the lambda should be yet. I'll start off with 1 again. And yeah, I want that point to go up to wherever, so the original, let's see, I think I called it V91. Okay, so the original vertex location at J. I'll keep the x coordinate as it is. So at this index 2, 4, 5, 0, I'll keep the x coordinate as it is, but I want to move the y coordinate to be 0.8. I'll keep the z coordinate as it is. Okay, so I'm going to try to raise that finger up. At the same time, though, I do need, like before, like the figure 8, I'm going to need to fix some other anchors to keep other points in the same place. So maybe I'll anchor down the feet here. So I'll keep, okay, so vertex 6, 6, 4, 7. I want that to stay where it is. So I'll say, okay, vertex, maybe I should make this a variable because I might want to change it for all of them. But I'll say vertex 6, 6, 4, 7, stay where you are. So yeah, actually I'll just slice that out. Stay where you are. I'll pick just a couple more. So I'll keep that foot there, maybe I'll keep the other finger there, and then maybe a point in the head. Okay, so I'm going to keep 5, 9, 8, 8 where it is. And then, so 5, 9, 8, 8. And then finally, let me keep a point on the head where it is. So pick a point up there, vertex 4, 11. Okay, so 4, 11 should stay where it is. All right. So yeah, the mask, I don't know exactly what to make that yet either, but so it looks like this guy's about 1 meter tall, or maybe a little more than that. So probably, let's say maybe within 20 centimeters, I still want to try to preserve, yeah, it's interesting because this is going to be, okay, actually, this is a little tricky. So I think I want to use the distance matrix of the original point cloud in Euclidean space, but I want to use the mask based on the geodesic, so it's going to be a little bit mixed here. So actually, okay, yeah, let me do that. So I'm going to say D91 Euclidean equals get dist map V91. Yeah, because I kind of want to keep it where it is in space. I want to keep the points relative to each other where they're on space, but only the ones that are near to each other. Okay, yes, so I'm going to try that. That's the matrix I actually want to reconstruct here. So it is actually a Euclidean matrix, but I'm going to put a mask on it, and I'm going to add these anchors. So yeah, the mask is going to be based on the geodesic distance. So I'll say, so D91, like I said, maybe less than 20 centimeters. Okay, so let's try that. So D91 Euclidean. Okay, so this is, yeah, it's going to do the math there. And I'll say anchors equals anchors. Okay, let me see if this runs. V1, I meant to say V91. Okay, so let me just clean this up for a second, I'll run it. So I got kind of an awesome result here. So if we go back here, probably, if I look at the loss function, let's see what happened there. So losses. Okay, so it did bottom out pretty quickly. Maybe I need to make these a little bit less stringent. Yeah, I'll play with this and let's see what happens. Okay, so here's the result now. At least, okay, it's definitely stretching. But actually, looking at the loss curve again, I see a little bit of this. I think the learning rate might be too high. I think I need to turn this down a little bit. Maybe have it go for some more iterations. So let me try that now. Oh man. Okay, so we're really not getting this. And I think the problem might be this is a pretty complicated optimization. And what I really should be doing is, I got to remember here, I'm using gradient descent. So the initial conditions are really important. So because I know I'm trying to basically reconstruct this thing, but using the original Euclidean distances, let me start off with an initial condition that is the original shape. So I'll pass along here V91. So I'm going to add a parameter here, which is, I'll call it x orig. So the original point. So rather than randomly initializing, I'm actually going to say x equals torch.from numpy x orig .to device. So let me allow that to be an initial condition, and let me go with that. It looks like it converged by about 500 iterations, so I'll just let it go there. See how we do. Okay, yeah, let me just take a second to clean this up. All right, folks, I think I might have to call it here. So I did get to raise actually both of his arms for some reason a little bit. But yeah, this is not really a typical way to do this kind of pose articulation. Usually you would rig the thing up and move the rig around, or actually there's another technique I like which doesn't require a rig called Laplacian mesh editing. One of these days I'll make a video on that. But yeah, I just wanted to try this and see how it would go. But yeah, hopefully you can see at least how flexible this technique is, so to speak. And now you see, I've given you a whole tour through multidimensional scaling. I've changed the title to Multidimensional Scaling Theory and Application. So we had the classic multidimensional scaling, and we had the p-stress. So I hope this was informative, and even if you'd seen multidimensional scaling before, I hope you understand a lot better how the techniques work. Thank you for hanging on this long in the video. I appreciate it. I will be back soon with more videos. Let me know what you think in the comments. And let me know if there's anything else you'd like me to teach. See you all soon.